Bismillahirrahmanirrahim. Dear students, in this video we will discuss how we find the eigenvalues and eigenvector of a 3 by 3 square matrix. So let's begin. Consider a 3 by 3 matrix A, and in order to find eigenvalues we first need to convert or transform this matrix A into this form, that is the determinant of lambda into I minus A equal to 0 for getting characteristic equation. So before going to solve this, I will discuss it as the lambda is basically a scalar value and the I is representing the identity matrix and its order will be the same as the order of A. As the order of A is 3 by 3, so this is the identity matrix of 3 rows and 3 column like this. So multiply lambda with I like this. It gives us lambda 0 0 0 lambda 0 0 0 lambda, and subtract it and subtract A from it, that is 1 0 minus 2 0 0 0 minus 2 0 and 4. Then take their determinant and equate it with respect to 0. Now if I see the order of both the matrices, both are 3 by 3, so subtraction is possible. So when I subtract it, it gives lambda minus 1 0, then minus 2 becomes positive, then we have 0, it's lambda 0, and then again minus 2 becomes positive 2 0, and it's lambda minus 4. Now with the help of cofactor expansion we need to find its determinant, or see if we expand with the help of column number 2, then there is a lambda value, and then we have skip this row and this column, we have lambda minus 1 2 2 and lambda minus 4 and equate it with 0. Now when we further simplify it, we have lambda multiply the mean diagonal elements like this, lambda minus 1 into lambda minus 4, and then it's 2 into 2 is 4 along with the negative sign as the property of the determinant. Now if I multiply this lambda minus 1 and lambda minus 4, it's basically lambda square minus 4 lambda and minus lambda plus 4, this becomes equal to 0. Now if I further simplify it, it gives me lambda square minus 4 and minus, it becomes minus 5 lambda, and this plus and minus gets each other. We have like this. We can take lambda as common from this bracket. So when I take lambda as common, so the lambda before this bracket becomes lambda square and the internal term becomes lambda minus 5 equal to 0. Now the thing that is very important, we have like this. When we convert this into polynomial, the highest degree of the polynomial is cubic basically. When I multiply lambda square into lambda, it gives lambda cube. So we will get 3 values of lambda, but here the value of lambda, that is 0, is basically a repeated value. So we have three values of lambda, out of which the zero value is basically the repeated value. And we have discussed that if we have a repeated value, then its algebraic multiplicity becomes equal to 2, and its algebraic multiplicity becomes equal to 1 because it's only one value. So now these are basically the eigenvalues. Similarly, we can find the eigenvectors that are also known as the basis for eigenspace. Now how we evaluate it? We just need to simplify the previous matrix like this that contains the lambda value, which is lambda minus 1. I'm writing this over here. Our matrix is this, that is lambda minus 1 and 0 2 0 lambda 0 2 0 and lambda minus 4. In order to find eigenvectors, we need to substitute lambda values in this matrix. See, I'm putting the first value of lambda, that is equal to 0. So if I substitute lambda as 0, my matrix, we call it as matrix A, for example. My matrix A becomes like this. It becomes minus 1 0 2 0 0 0, and it becomes 2 0 and minus 4. Now we need to convert this into echelon form. When I convert this into echelon form, we know that the second entire row is basically 0, so I can directly move the second row at the bottom, so it becomes like this 0 0 0. And when I simply do R2 plus 2R1, so it gives me a matrix like this 1 0 minus 2 0 0 0 0 0 0. Now this one is representing the leading variable, and here we have x2 and x3 as our free variables, so we are assigning parameters like s and t to our free variable. So the equation for x1 becomes 2x3, and in terms of parameter it looks like this, it becomes 2t. So we have these values. X1 is equal to 2t, and x2 is basically s, and x3 is our t value. So we can rewrite this like this. For t we have 2 and 0 and 1, and for s we have 0 1 0. We can write s before t as well, it's up to us. The order doesn't matter. So now see here, we have two basis vectors, so its geometric multiplicity is 2. Similarly, we can do the same for lambda is equal to 5. The next lambda value is 5, so we can do this for lambda equal to 5. So when I substitute this in my main matrix is lambda minus 1, 2 0 and lambda minus 4. Then now substitute lambda as 5, it becomes 4 0 2 0 5 0 and 2 0, and we have 1 here. Now what we need to do, we need to again convert this into echelon form. or you can do this in reduced echelon form as well. So its final form is this 1 0 1 over 2 0 1 0 0 0 0. Now here we have two leading variables and only the one free variable, that is x3. So we are taking it as t. Now I can write x2 and it here is 0 and x1 as minus 1 over 2 x3, and as x3 becomes equal to t, we are letting it t, so it becomes minus 1 over t. So in terms of vector, we have x1 x2 x3 like this, minus 1 over 2, we can take t as common, 0 and 1. So here we have only one vector, so its geometric multiplicity is 1. Now I want to highlight one very important point, that for lambda is equal to 0, the algebraic multiplicity is 2, because the lambda 0, the value of 0 is repeated and it gives two vectors, so its geometric multiplicity is 2. Similarly, for lambda is equal to 5, the algebraic multiplicity is 1 and its geometric multiplicity is also 1. So as these are equal, so our matrix A, that is our main matrix, our matrix A is diagonalizable. We can diagonalize it. Now we need to gather these three eigenvectors in the form of a vector P like this. For lambda is equal to 0, we have two vectors. We can write this combined in the form of matrix like uh, 0 1 0 and 2 0 1, and for lambda is equal to 5, we have one more vector, that is 1 over 2 minus and 0 and 1. So this is our matrix P. As their geometric multiplicity and arithmetic multiplicities of each eigenvalues are same, so our matrix A is diagonalizable. Diagonalizable means if I'm taking P inverse and multiply it with A and then P, it gives me a diagonal matrix, and the diagonal contains the eigenvalues like this 0 0 and 5, and the other entries are 0. You can evaluate the inverse of P and its entire multiplication with the help of the other uploaded video in class with calculator series from my channel. So you can also go through it, how we find the inverse of any matrix with the help of scientific calculator. So these are basically the concept where we have eigenvalues, we see how we evaluate the eigenvectors, and in the last, if their geometric and algebraic multiplicities are same, so we say that we can also diagonalize matrix A with the help of this formula, that is P inverse AP. Hope this video is clear.